About 1,000 years ago, in 1181, a rare celestial event, a rare explosion lit up the sky. We now may have finally found out what it left behind. For 900 years, scholars and stargazers, astronomers sought to explain a bright cosmic object. It briefly lit up the skies over China and Japan in 1181. A new study may solve the mystery that has lasted this long. The nebula PA30, named Parker's Star, is one of the hottest in our Milky Way galaxy. And the star it surrounds are much of the phenomena observed in the sky all those years, according to measurements of its modern day position, the expansion speed, and the state it's in. Observers show that the cloud of gas and dust that is PA30 is expanding at a rate of a huge 684 miles a second. That suggests it originated from a central point about 1,000 years ago, most likely from a supernova explosion. This may well be what was observed by contemporary astronomers back in 1181, a supernova explosion. The historical reports place the guest star between two Chinese constellations, Chuanshe and Huagai. This is according to astrophysicist Albert Zijlstra from University of Manchester in the UK. Parker's star fits the position well, which means that both the age and the location fit the events of what was observed in 1181. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below. The stargazers of the 12th century reported this object in the sky as bright as Saturn, and it was also visible for a whopping 6 months. They also made records of its position in the sky. Astronomers have since used observations to come up with a few conclusions, theories, hypotheses about have not been able to confidently pinpoint what it left behind up to now. PA30 and Parker's Star are believed to have been created by the merger of two small, dense white dwarf stars. It's a rare occurrence, leaving behind what's known as a type lax supernova or a zombie star. It's a rare category of supernova that scientists are still learning more about, and what's even rarer is having information about how the supernova started as well as the remnants it has left behind. Zijlstra says only around 10% of the supernovae are of this type. They are not well understood. In fact, the fact that SN 1181 was faint but faded very slowly fits this type. This is the only such event that we can study both the remnant nebula and the merging star and also have a description of the explosion itself. Since 1006 AD, there have been 5 bright supernovas spotted in the Milky Way, and astronomers already found matches for the other 4. One of them, known as the Crab Nebula in the Tarsus constellation, is also thought to be around 1,000 years old. So that's pretty new. Now, the first discovery in 2013 seems that PA30 now completes the set. It was discovered in 2013. Before now, there had been some debates about whether the merger of 2 white dwarf stars could result in a supernova like this. So the discovery has plenty to teach astronomers about other similar supernova explosions as well. Zijlstra says this is a type lax supernova, the only type lax supernova where detailed studies of the remnant star and nebula are possible. It's nice to be able, he says, to solve both a historical and an astronomical mystery. So they found it, didn't they? This is published in Astronomical Journal Letters and by David Neal at Science Alert.
About 2 or 3 times a century, a massive star in our galaxy explodes. The star's core may survive as a neutron star or a black hole, but the rest of it rushes into space as swiftly expanding debris behind a powerful shockwave. As the supernova remnant grows, it sweeps up interstellar gas and gradually decelerates. Yet even thousands of years later, its imprint on the galaxy remains impressive. Exploding stars and their remnants have long been suspected of producing cosmic rays, some of the fastest matter in the universe. Where and how these protons, electrons, and atomic nuclei are boosted to such high speeds has been an enduring mystery. Now, observations of 2 supernova remnants by NASA's Fermi Gamma-ray Space Telescope provide new insights. Because cosmic rays carry electric charge, their direction changes as they travel through magnetic fields. By the time the particles reach us, their paths are completely scrambled. We can't trace them back to their sources. So scientists must locate their origins by indirect means, which is where Fermi comes in. The interaction of high-energy particles with light and ordinary matter can produce gamma rays, the most powerful form of light. Unlike cosmic rays, gamma rays travel to us straight from their sources. In 1949, physicist Enrico Fermi worked out how what he called magnetized clouds could accelerate cosmic rays. Later studies showed that a variant of his method, called Fermi acceleration, worked especially well in supernova remnants. Confined by a magnetic field, high-energy particles move around randomly. Sometimes they cross the shockwave. With each round trip, they gain about 1% of their original energy. After dozens to hundreds of crossings, the particle is moving near the speed of light and is finally able to escape. If the supernova remnant resides near a dense molecular cloud, some of those escaping cosmic rays may strike the gas and produce gamma rays. But electrons and protons make gamma rays in different ways. Cosmic ray electrons do so when they're deflected by passing near the nucleus of an atom. Accelerated protons may collide with an ordinary proton and produce a short-lived particle called a neutral pion. These pions quickly decay into a pair of gamma rays. At their brightest, both types of emission look very similar. Only with sensitive measurements at lower gamma ray energies can scientists determine which process is responsible. Now, Fermi observations have done just that. They conclusively show these supernova remnants are accelerating protons. When they strike protons in nearby molecular clouds, they produce pions, and ultimately, the gamma ray emission Fermi sees. NASA's Fermi has detected gamma rays from many more supernova remnants, but the jury is still out on whether accelerated protons are always responsible, and what their maximum energies may be. Nevertheless, the Fermi team has taken a major step, a century after the discovery of cosmic rays, in establishing just where they arise. Something that would satisfy, but certainly not surprise, the original Fermi.